talk about population ecology. Ecology is like the biggest kind of biology. It encompasses everything. We're going to go through today talking about individuals and how they fit into populations or groups of the same species, and then we'll work our way all the way up to everything on the earth. Ecology is the study of the relationships between living things and the environment. So basically, how living things interact with, sorry, it's in the beginning. Yeah, thanks. The beginning of your book is ecology. I know you thought you were finished with the book last week. It's the very beginning of the book. That's where we start. So ecology is the relationships between organisms and their environment. So it can be, ecology encompasses how you interact with members of your same species, members of other species, things like air and water, things like acid rain, climate change. So it's just every interaction you have with everything around you is ecology. What does biology mean? My biology majors, what's the definition of biology? Is it the study of the earth? That's geology, right? The study of animals? Zoology, right? You go to the zoo, see animals. Zoology. The study of natural processes? I mean, that kind of thing sounds like maybe more ecology, something in ecology, but not ecology. The study of non-living things? Is what? Yeah, maybe paleontology, right? They're not living anymore. This, chemistry maybe, right? The study of living things. Yeah, okay. So living things, that's the B-I-O. Anytime you see bio in a word, it refers to there's something living about whatever you're talking about. The L-O-G-Y means the study of. So like zoology, zoo, animals. The lology part, lologing part is the study of, so the study of animals. All right, so when we're talking about ecology, we're talking about the living things and the way other things interact. So if we encompass that in terms of the B-I-O part, it's the biotic things. Biotic means living components. There's that B-I-O again. And then non-living parts are the A. A means without or no. And then there's that B-I-O again. So non-living things is abiotic. The basics of population ecology encompasses 4 ideas here that we're going to go through. 4 questions we're going to answer through this lecture is how do populations grow? What limits or regulates the growth of populations? How are populations distributed, meaning like how big or small they go around their area or around the earth? And then what about the human population? One of the things about the human population when we're talking about strict ecology is that because humans have technology, we can defy the laws and rules of what happens in more natural populations. So for example, if we get into an area and it starts to get overcrowded, we can build tall buildings to house a lot of people in a smaller footprint or space on the ground. Whereas a lot of other species, they can't do that. Or they can only do it to an extent, like a wasp nest, right? Wasps will build those circular nests, and they can get to be like the size of a beach ball, but that's about it. So they don't build nests that are as big as buildings are. So we definitely can defy things. Also, in terms of just thinking about illnesses, we have medicines. And to some extent, natural populations have ways to deal with illness, but not like we do. We have a lot of interventions. We have hospitals. We have people who go to school, like some of you, to help other people to recover. A lot of natural populations don't have that. The other one I just want to mention in terms of like technology is our food systems. We have a lot of technology to help us to have food for so many people. Whereas in natural populations, they might have food in a certain area, and once it runs out, well, that's it. But we make different plans for them. So again, we're talking about in this first section, we're talking about what happens in natural populations, like the population of turkey vultures that live in this area, or the population of ants that live out in the prairie. Population growth, when we're talking about a population means all the members of a species that live in the same ecosystem, so the same area, right now, at the same place, at the same time. So, if we're looking at our prairie out there, there's a number of different populations out there. There's different kinds of fungus out there. There's different bacteria out there. There are birds that pass through temporarily. There are some birds that live there all the time. There's mice and muskrats, and there's even coyotes that live out there. We are kind of like a population, but again, we can kind of like go places, right? We can change. I know a lot of you are going overseas for the summer to visit family, so then you'll go from being a member of this population and in the summer, a member of a different population. The other thing about populations that's really important, and when we're talking about species, and if you remember back to when we talked in evolution, that the important thing about evolution in regard to species is that they can potentially interbreed. And so a population or a species of members who live in the same place at the same time, they can have sex with one another and have offspring who are fertile, meaning that their offspring can also have offspring and keep that group going in that place right now. So there's a lot of things about a population that are important to remember. Same species, which means that they can reproduce and keep that group going over time, and they have to live in the same place at the same time. So a species of, let's say, turkey vultures that lives here is a different population than the ones that live near the lake, because they don't live in the same place, they don't interact. So they're different populations, even though they are the same species. Factors that influence how a population can change over time are the number of births in the population, the number of deaths in the population, and then we'll talk a little bit about migration. Who comes in and who comes out of that population? Yeah.
So the population is all animals, or just one species?
It's one species that lives as a group in the same area. So not necessarily just animals, but it could be bacteria. And a population could be the bacteria. Your microbiome, for example, has a community, and we'll get to community next. And what community means, it means all the species that live together, all the different species that live in the same place at the same time. So like our microbiome, all the microorganisms that live in and on us, that is a community of them. And let's say if we're talking about a strain of E. coli that lives in your digestive system, that would be a population of E. coli within us. So migration, there's two parts to migration. There's immigration. When you're talking about immigration, or think about like immigrants, they come from somewhere else and they join a new population. Sometimes you can have members of a population that move out and they're immigrants, and we call that emigration. Emigration is leaving, immigration is joining. in general, when we're talking about population numbers, populations are stable and not perfectly like, let's say there's 1,000 members of a species that live in the same place at the same time, that year to year there's always 1,000. That's, maybe it'll go like 1,000, maybe it'll go to like 1,080, maybe the next year it goes down to 960, and then maybe the next year it goes back to about 1,010. So what you see is that over time, it's about the same amount. It might hover at a line that it kind of comes back and forth through. So it won't always be exactly equal, but it'll be close. Populations are stable when you have about the same number of individuals joining that population as you do leaving. We have a few ways that populations can join and leave. Populations get larger if the number of births and immigrants, those that are joining the population, are bigger than the number of deaths and emigrants, those that are leaving the population physically. Populations get smaller if the opposite is true, meaning that you have a lot more deaths and emigrants than you have births and immigrants. This idea here of just talking about the numbers that are coming in and out refers to, we're going to talk about two different concepts in terms of population and what influences the size of a population over time. And one is this kind of idea where we're talking about the individuals joining or leaving. And that's what we call biotic potential. The potential of the living things to influence the size of the population over time. Eventually what's going to happen with biotic potential, or this idea of, like, let's say that it keeps getting larger and larger and larger, population gets larger, and eventually they run out of space or food, or there's a lot more competition, predators start to see them. So then once you have a lot of biotic potential and you're getting larger, you have this other thing that comes and says, nah. And it's not just one thing, but it's a whole bunch of things. And that is what we call environmental resistance. That as populations grow, the environment resists them to continue. So we have this biotic potential and we have environmental resistance. And these two factors will determine the size and shape of a population over time. This first part of the lecture, we're going to concentrate on the biotic potential. Second part of the lecture and the next lecture, we're going to talk about that environmental resistance that stops the population to just get larger infinitely. We can figure out how much population is growing year to year, or the annual growth rate. We might, depending on the population and how quickly they reproduce, the annual growth rate could be referred to like year to year. Let's say that we're looking at those turkey vultures. And we're going to see from year to year out here around Moraine Valley's campus, how many turkey vultures do we have every year? We're going to track that. Could be in our body, if we're talking about E. coli bacteria, and let's say that they can replicate every 30 minutes, we might look month to month at that population. Or even if you have, let's say, streptococcus in your throat, and you have a strep throat, we might look at the growth of that population day to day. So when we're talking about growth rate, it might not only always be annual, year to year. If you're doing a study, it might be a different category in terms of time. The equation for your annual growth rate are the births minus the deaths. So we're going to put those together because they have a huge influence on the growth of a population. And then we're going to look at the immigrants and the emigrants. In natural populations, the migration factor doesn't have a huge influence. The only time it might have a huge influence if something really crazy is happening, that you suddenly have like the growth of the population and a huge amount of maybe one or many environmental resistance factors comes and says, and some of them may migrate away. natural populations, again, we're talking about natural populations. Birth and death are more significant. With humans, we can defy that because we can migrate a lot easier, right? If we all said, oh, things are looking really good on the Solomon Islands in the middle of the Pacific Ocean, that they have all kinds of great resources in that community, and we're like, let's go there. Let's all go and live there. And we can take an airplane and get there. Most other populations or individuals in a population, they've just got to go on their feet with their wings, with their fins to move. And so it's a lot more difficult to migrate. So natural populations, birth and death are the most significant factors. So what influences birth and death? As I mentioned, biotic potential will. Biotic potential is based on having lots of good resources so that you have a lot of space and you have a lot of food and you are not competing for so many things. But everybody's kind of like, okay, we all have our jobs, we're going to contribute, we're going to help our population grow in this area, we're going to have a lot of babies because there's a lot of space and food, maybe not a lot of predators, but conditions are really, really good. That's biotic potential. When you have relatively unlimited resources, and then you're just popping out those babies, that you're having good reproductive factors in the environment. This is where you stop eventually. That when the unlimited resources start to become limited, that's your environmental resistance. And again, food, space, competition, predation, sickness. You get a lot of crowding, you can spread diseases much faster. Natural events. Every day we're hearing about a new natural event that has an effect on some ecosystem. Like the sandstorm, dirt storm that came through the middle of Illinois yesterday.
This big accident.
Oh, there was like
22 cars and like almost 12 trucks went.
yeah,
Yeah.
semi-trucks knocked over all over the place, huge accidents. And that all of that was brought in the windstorm. There was a lot of sand. I'm guessing it's probably a lot more dirt than sand, but has an effect on the natural populations too. Can cover up plants so that they can't photosynthesize as well. And so we're going to have an effect then on everybody else in the ecosystem who relies on plants. So we're going to focus on biotic potential for a while. Biotic potential, again, B-I-O, potential. The potential, the unlimited ability of the living things. We usually look at it as an idea of changes in individuals per a unit time. How many individuals in that population? Now, how many individuals in that population next month, next year, over 10 years? So we're going to look at some kind of unit time and then see how many individuals we have. When we look at biotic potential, one of the things that we like to study is growth rate. Growth rate is a italics little r. If we're looking at a rate, we're looking at some kind of percentage. Growth rate is B, the birth rate, the percentage of births, minus the death rate, the percentage of deaths. And again, in natural populations, migration doesn't have a huge effect. So when we're looking at growth rate, we're just going to focus on births and deaths. So let's take a look at a population of mice. The size of the population is 10,000 to start with. In the first year, we have 500 deaths and we have 1,500 births. So good biotic potential. We can see that the births are outnumbering the deaths. So when we calculate birth rate, we're going to take 1,500, the number that were born, divide that by 10,000, and we get 0.15. And when we change that to a percentage, we're gonna times by 100, and what we get is 15% births in that population in that first year.
So B equals birth divided by population size?
Yes. Right. B is births divided by population size. D, the death rate, we're going to take the number of deaths, divide by the population size, 10,000, and we get 0.05. We can change that to a percentage by timesing by 100, and it tells us we had a 5% death rate in that first year. Now we're going to put them together. We're going to take our birth rate, we're going to subtract our death rate to get the annual growth rate. So I think you can do this math. That remembering that our calculation is R, the growth rate, is B, the birth rate, minus D, the death rate. So for the first year, R, or our annual growth rate, would be what? So yes, remember you're taking B minus D. So that tells us when you take 0.15 minus 0.5, you get 0.10, or when we say 0.10, we times it by 100, and that gives us 10% growth rate in the first year. That's pretty good, right? If we're thinking about the size of the population, if it's growing 10%, we're adding that percentage on every year. So now, when we take our 0.15 and our 0.05, subtract 0.05 from 0.15, the B minus the D gives us the growth rate of 0.10 times 100, gives you 10% population growth per mouse per year. The original population size is N. Remember that that was 10,000. Our population growth, we can take our initial population size of N, 10,000, times our R, our growth rate, which was 0.10 or 10%. So if you do the math on that, you take R times N, how many individuals were added to the population in that first year? Remember, you're taking R, 10% times N, 10,000. Yeah, so you get 1,000. That's a lot of individuals. Again, 0.10 R times 10,000 is 1,000 new mice in the first year. Now, if we take our R for the second year times our N, do we have a new N in our second year? Did we not just add a whole bunch of individuals? Okay, so take your new N times our initial R, and tell me how many individuals are added in the second year. Remember, R was 0.10. Our N, we took 10,000 plus 100, which gives us 11,000. So R, 10% times 11,000 is 1,100. So again, in our second year, we took our 10,000, our original N, plus 1,000 new individuals, which gives us a new N of 11,000. So R times N in the next year, 10% times 11,000 adds 1,100 individuals. So even in the second year, we added 100 extra beyond our first year. And so one of the things that you might imagine is that that number in that population goes like this and starts ticking up. And at some point, you kind of get this critical number of individuals who are reproducing, and it starts to really shoot up. This shows us often that when you have a population who's moved into potentially a new area where there's just unlimited resources, lots of space and food, and there's no predators, not much disease, things are really easy living, that your population can show quick or rapid exponential, meaning that they go tick, 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 eventually really quickly upward exponential growth. This means that that population is just accelerating and accelerating and accelerating. And when we graph this, as I've been showing you, it kind of goes like this. So we have that J, starts out low, and gets to this curve, and then just shoots up. And so that when you graph over time, your Rn every year, and you graph, it's gonna go, it's gonna go really high. And it's gonna show what we call a J-shaped curve, or an exponential growth curve. So here, if we're talking about bacteria, this is very common in terms of like a strep throat, for example. That, let's say you go to class and somebody just coughs into the air, and you breathe in as they're coughing, and you get some strep bacteria, and you are susceptible to a streptococcus infection in your throat, that what can happen in a matter of hours is that in your throat you get 1, and then it replicates to 2, to 4, to 8, to 16. And eventually it's like doing a little exponential growth in your throat. So anytime you see this shoot up of a population, we call this the biotic potential. It's the, again, the potential ability of the living things to expand or reproduce and go up in an area. Depending on how quickly the bacteria can replicate, also could be just the resources that you have. If you're drinking something that's very acidic, like let's say you're drinking a lemonade, and the streptococcus doesn't grow well in an acidic environment, maybe it'll take that strep a little bit longer to start to show that exponential growth. Or let's say that you're drinking something like, I don't know, let's say milk-based, and it does really well with the milk carbohydrate. It could grow quicker in your throat. You could start to feel the effects of that quicker. So this one I just want to mention again, that when we're talking about these exponential growths, it doesn't mean that it'll take years necessarily. It could take a matter of hours when we're talking about some organisms. But if we're looking at something bigger, like an animal, like we see here, these eagles, the eagles may take up to maybe between like 17 to 27 years to start to show that really quick biotic potential. Some of that is influenced at the age of reproduction. So if you have 2 different species of eagles, or even the same species, again, depending on like what's happening in the environment, that let's say that you have one species that can begin reproducing at the age of 4. Their biotic potential is going to happen much earlier, because individuals who are born can begin at the age of 4 to add more individuals to the population, in comparison to a population where they begin to reproduce at the age of 6. So now you've got 2 more years before your new individuals can add to the population in terms of numbers. What's R again? Yeah, good. R, again, it's growth rate. Growth rate is the birth rate minus the death rate. And we don't see migration because in natural populations, migration is not a significant factor in terms of biotic potential. With biology, there's always exceptions though, that you always have something weird. Like if we're talking about mammals and saying mammals have internal births inside of a uterus, and then you have something like the platypus who does a birth in an egg, and the birth is external and not inside of the uterus, but for reasons because of their genetics and because of other factors, we classify them as a mammal. In biology, it's always an interesting thing, and one of the things that you will all experience in your pathways going forward is that sometimes you come across something and it's different than what the textbook says, or what you learned, or what you even know about that group of organisms, and it does something different. Populations evolve, which means that mutations happen by chance. And as biologists, you're all going to be future biologists in some field of biology, that you have to realize that things change. And sometimes organisms don't follow the rules. So you'll have to solve those mysteries. That's one of the things I love about biology, is that you're always learning new things. So exponential growth occurs when the births greatly exceed the deaths. A lot more coming into the population than are dying. A big influence on that in terms of individuals is that when you have a population that can add more than one offspring to the population over time, over their lifetime, you can see that exponential growth happen quicker. Thinking about population growth, that when you as an individual, or you as two individuals in the population, right, a mating pair, that when you have a mating pair and each one only has one surviving offspring, that you have two individuals, and if they have only one surviving offspring, there's two that goes down to replacement with one. So that can cause your population to get smaller. When you have a mating pair and they have two offspring, they're each eventually replaced. When you have more than one for each individuals in a mating pair, that this mating pair now has three. Now they're being replaced by their two, plus they're adding an extra one over time. So when a mating pair has more than two offspring, it has significant effects on the growth of the population. So biotic potential depends on, as we looked with the eagles, the age of first reproduction. So let's say that you have two eagles, and one eagle mating pair, they have one offspring, and they only have that one offspring when they're 18 years old each. So much later. In comparison, you might have a mating pair who begins mating at the age of 4. They have a lot more potential over time to add to the population. Let's say that population, or that mating pair, the mating pair that started mating at the age of 18, they only have one individual, one offspring. But the mating pair that begins at age of 4, they have, let's say, a clutch of 3 eggs every year. So they start at the age of 4, every year they add 3 potential new individuals. The other pair only has 1, and much later in life. So number of offspring that you can contribute with each mating cycle is significant. And let's say that our mating pair who mated at the age of 18, they had 1 egg, and that egg didn't develop fully. So they end up not contributing any offspring to the population. But let's say our other mating pair, they begin at the age of 4, they have 3 eggs every year. Every clutch of eggs, every 3 eggs survives. So in 10 years, they add 30 individuals. Let's say they mate for 20 years. They can add 60 individuals. By the time, if they can start mating at the age of 4, so when they're 8, their first offspring can begin mating themselves. So they can really add to the population. So there's a lot in terms of when you mate, how often you mate, how old you are when you mate, and if your offspring survive so that they can add to the population. Those all are factors that are going to influence how big a population can get. There's other things that influence a population. So now let's talk a little bit about environmental resistance. That when you have a population and they show that biotic potential, if you look here, between here and here, this shows you the shape of a J. Then here, you have that J-shaped exponential growth curve. But something happens, bam. Nutrients, they run out of food and energy and atoms that are available. Environmental resistance stops the biotic potential from continuing. Now, depending on, there's a lot of factors, how much environmental resistance happens. Here we can see there's something significant, maybe not. And when we talk about nutrients, nutrients include energy, water, air, sunlight. So all of those things in terms of nutrients can encompass a lot of ideas that could prevent them from continuing to exponentially grow. What happens is environmental resistance kicks in and you have a bust or a crash in the population. This is a good example of what happens like out on our prairie and in our area of the country, of the world, every year. That about May, really June, things get good again. In terms of availability of space, everything is kind of like over the winter. The numbers in a population have gone way down. So that now, especially like you see on the prairie, there's things that are starting to grow because everything has, the top parts of the plant matter has died off over the winter. The roots are like, oh, it's been raining a lot, hasn't it? So that's a big significant thing in our area of the world in the spring, is that rain or water, which is a very significant factor in making photosynthesis go quickly, is we need water and we need sunlight and we need carbon dioxide. So we've got these three things that when it starts to rain a lot and the weather gets warmer and you've got more space because all the plant matter has died down over the winter, that you've got a lot of very favorable conditions for all those plants out there to grow more and grow better. When you have plant matter to eat, all of the other populations, fungus and the bacteria and the animals, everybody else starts to go, oh, yeah, we got a lot of food. So then they start to also take off. And we have good things happening over the summer because you've got all of these resources available. But then the weather changes again. And the days get shorter because the tilt of the earth. It doesn't rain as much late summer, it's hot. And it starts to get colder. And so we have all these things in terms of like, not just nutrients, but other factors that are like, bam. You also get crowding. That conditions are good, but everything gets crowded. There's only so much space on the prairie. So all of these environmental resistant factors make that population start to die back. Now, do they totally die off in our area? For the most part, most of our populations have evolved adaptations or strategies for survival in the conditions of winter here. So that a lot of them will go dormant, or the plant matter at the top will die off, but the roots, we have tap roots here. We have a lot of dicot plants, and so then their roots survive deep in the ground where it's warmer. The trees lose their leaves. They don't spend a lot of energy on growing leaves. So Then a lot of the animals and the fungi and the bacteria, they all have strategies for surviving over the winter as well. A lot of animals will burrow. And so they survive at a very low level over the winter. Then next year again, about this time, conditions become favorable and they grow again. So here, this is kind of an interesting graph in that there are a lot of organisms who live in conditions like ours where we have seasons, and you see this graph happen every year, where you have eventually that biotic potential, environmental resistance kicks in, you have a crash or a bust, and then back to existing at a low level over time. We might see this in populations in terms of that boom and that bust, or growth and crash. It might take like 40 years for it to happen, not a yearly thing. So there was a study done on reindeer in an area where in 1910 conditions weren't very good there, but there were opportunities for growth and biotic potential. And so we saw between 1910 and about 1935, we see that J-shaped curve. It's never perfectly J-shaped because maybe something happened here at about 1922 where conditions got really, really good, but then something, maybe there was like a virus that went through the population. And we saw some of the population die back a bit, and then they recovered again. So you might have these little blips when you study a population over time where it's good and then some little environmental resistance hits them, and then they go back to exponential growth. Then what happened about 1940, maybe 1935, 1940, that population got really, really dense. And then humans started to, we had the Industrial Revolution happening here. Humans start to populate an area, and so we have a lot of environmental resistance that occurs, and that population crashes to a point where they almost go extinct. So we have really three scenarios that can happen when we're talking about when environmental resistance kicks in. So let's look at the red. The worst case scenario, excuse me, that you have good J-shaped curve, good biotic potential, environmental resistance kicks in, and your population either almost dies out or goes extinct. Excuse me. The second thing is let's look at blue. So blue is, again, similar, great biotic potential, environmental resistance kicks in, and then they drop not quite as badly as the red, excuse me, and they recover. Now, they recover in terms of their potential. One of the things that we look at with a population's potential over time in an area is the carrying capacity or the ability of the environment to support that population for long periods of time. And so even though whatever we're talking about this blue, maybe their carrying capacity was like up here. But because of the environmental resistance factors really hurt them, that their carrying capacity starts to level off lower than it might normally do.
So basically, the carrying capacity is like directly linked to the resources that are kind of like depleted and that cause the resistance in the first place.
Yes.
Like you're getting all that resistance because there's like, I don't know, maybe no water.
Right.
So the carrying capacity is like directly related to the fact that there's no water.
Correct.
Okay.
Yes. Yes. And carrying capacity, we're going to define that next, is that carrying capacity means how much or the level of that population that can be supported, the amount of individuals that can be supported indefinitely for a long period of time. So they kind of level out a little bit lower than they might normally do because, like you said, maybe water. There's not enough water available, so they level out here. If water is available, they might go, and here's kind of an interesting thing, is that there are a lot of populations, especially of like bigger animals who live a long period of time. They often will show a smaller J-shaped curve, and when environmental resistance starts to kick in, they kind of put the brakes on the reproduction and instinctively just say like, oh, wait. Instead of fighting that environmental resistance to a point where it's gonna really hurt your population, they start to get uncomfortable, things start to get limited, and they're like, let's slow down on the reproduction. Let's slow down on the growth. And so they start to dip down, but then they're like, okay, we slowed down at the right time before everybody was really hurt so much in our population that we can start to level off at a place that's comfortable over time. And then again, you have those ups and downs, but it kind of like over time levels out at what we call the carrying capacity.
So like, as the carrying capacity gets like reduced and stuff, it's like kind of like that fluctuation, and it's, they're trying to level up. Does the populations, like maybe of like an animal or something, do they kind of know that there's limited resources and stuff, so do they kind of like try to hold back on producing offspring, or do they just like stay in La La Land and still try to reproduce even if there's not enough?
Right, so this is like that La La Land, right? They're like, oh, I know things are getting hard here, but let's just keep like pumping them out. I don't know what the instinct factor is, if it's genetic or what, or if they have a language to each other in a population. There's so much about other organisms that we don't know in terms of communication. A lot of people study that, like even fungi. There's people who study the way that fungi communicate with one another and how they do it. So why this happens and why this happens and why this happens, it's, go study it all, right? Like, so there's a lot of wonder about, are there conversations? Is it instinctual? Who knows? Good question. So the carrying capacity, again, it's a maximum number in a population that can be supported by the ecosystem in that area indefinitely, meaning for a really, really long period of time. That you have about the same number coming in as you are coming out. You have them about the same number of individuals using resources, contributing to the community, so that you don't get this crash in the population. All of these environmental factors affect the carrying capacity. So space especially, you run out of space. As humans, we're like, all right, let's get really crowded out here in Orland, so let's just start to build bigger buildings. Nutrients, which accounts for a lot of things, anything with atoms, water, sunlight. So again, you have those two factors. You've got the biotic potential, and then you've got the environmental resistance. Environmental resistance can be like bam and really push down the biotic potential, or it could be like, oh, okay, we're starting to get uncomfortable. Let's level out at our carrying capacity. So it's almost like there's like that fight, that natural fight in any population, is that do we keep growing or do we like deal with our carrying capacity now? I mean, our environmental resistance now, so that we're comfortable for a long time, or we just, like Emma said, go La La Land, just keep going, keep going, keep going. So just to reiterate that it might not be like the reindeer, where it's like just one event that happens over a long period of time. It could be that it's a yearly thing. Could be seasonal too. Could be in your throat. Could be in a matter of a week. So the time amount will vary depending on a species. And then here you can see these little lemmings, like a little rodent. Then over time, they have these boom and busts constantly and quickly. Looks like about every 5 years, they're doing a boom and bust, boom and bust.
It's like a mouse guinea pig.
Yeah, so what does that say about that population and their instincts for survival? So again, the thing that is going to counteract biotic potential is all of those limitations in the environment, environmental resistance. The environment resists the growth of a population. So just think about, sometimes in biology, like sometimes, the names tell you. Just think about what the actual words mean. Populations who have a good instinct for survival will stabilize. If they don't have that good instinct, they crash. And it could be just something, a whole bunch of factors at the same time happen, and things are good, and they're like, we still are not to our carrying capacity, and then a bunch of environmental resistance hits them at once. So it might not necessarily be, when we're talking about crashes, just instinct. It could be just a lot happens, bam. Like a tsunami comes, and that huge wave of water, it's unexpected, and it just like wipes all the nutrients and living things away from that area. Hopefully, populations they reach a limit and then they go to their carrying capacity. Crowding, space is a big factor. Diseases, as you have more individuals in a population, it's much easier to spread diseases. Sometimes you might get some emigration, that when you're getting really, really high and you have a lot of biotic potential and it starts to get crowded, there's diseases, there's competition for limited resources. Some individuals in that population are like, I think there might be a population not that far away that isn't experiencing all these negative environmental resistance factors, let's go over there. So sometimes they may emigrate. Sometimes individuals begin to die at a younger age. So when you have that crash, you get a bunch of deaths happening, much younger than normal. And then you might also have just individuals in the population are like, oh, it's getting uncomfortable. I don't think we should reproduce. And they stop reproducing. And the why of that all, who knows? Depends on the psyche of that organism. So stabilization is ideal at the carrying capacity. All of the factors in the environment that can support that population for a really, really long time without that population suffering. So what you have at that carrying capacity is that line, you're never gonna have a population that just exists like right straight across. That they always have 10,000 individuals every single year. Because from year to year, you might have some changes. Like one year you might have a ton of rain, which allows for, and just the right amount of a lot of rain, that allows for extra plant growth. So they have extra food, they have extra resources, less competition. So they're like, oh, we can reproduce a lot more for the next couple of years. But then maybe it gets crowded again. And the rain doesn't come as much the next few years. So then there are like a lot of deaths or lack of reproduction, and it goes down. And then they're like something, less crowding, for example, less competition, and it goes up a little bit. And so they hover at about equilibrium. But rarely are you ever gonna have a population that just is like at a distinct equilibrium. It'll be around that. And if you added over time the ups and downs of a population, it would be about zero growth over a long period of time, or a long period of study. When a population levels out at the carrying capacity, they have exponential growth, good biotic potential, and they start to show that J, but then at the carrying capacity, they start to do this, right? So now we have a different shape of our population growth. It goes like this, and then it goes like this. So that J turns into an S over time. And so here, we call this an S-shaped curve, because it mimics more of the shape of an S when a population levels out at their carrying capacity. But you do start to see that J right here. So they show that exponential growth, but then level out, and it becomes an S-shaped curve. This is like textbook, like they will level out at the carrying capacity, but that rarely ever happens. And what you have up here that's limiting this from going higher is you have environmental resistance. It's always kind of hovering and pushing that population to stay at the carrying capacity.
The difference between the logarithmic, the J curve and the S curve is like, how much environmental resistance there is? Like when
Yes.
In the J curve, there's a lot of environmental resistance, like all of a sudden versus something that's like maybe a little environmental resistance over a period of time.
Potentially. It's hard to necessarily say how much of it is instinctual, how much of it is cognition, how much of it, like when the environmental resistance hits, like what causes them to go this way as opposed to just ignore it. And that's why humans, we're so different. But natural populations, it's hard to, the why is hard to say, but yeah, definitely. When that environmental resistance begins to just like hover, you're like, okay, we'll stay away from you and we'll just be down here. So again, environmental resistance, the maximum size stops the exponential growth from happening. Maximum size of the population that can be supported for a long period of time. Thinking about more comfortable. So all of these things are influences on that. One is renewable resources. Anything that can be made over and over again, so it's readily available. So like rain, right? We have precipitation, and we have evaporation, precipitation, and so that is a big renewable factor because we know it goes away and it comes back, it's renewed. Sunlight, day and night, right? Sun goes up, sun goes down, sun goes up, sun goes down, there it spins. Inorganic nutrients, carbon dioxide, for example. And then these things, right? These things make food. All of those things can be renewed. They can grow. Carbon dioxide is always around. Water available. Nutrients, things die, right? Things die, the decomposers and the detritivores break down the nutrients in living things, make them available to the plants, and we have these cycles that happen. Non-renewable resources, space, running space, gets crowded. So this is going to be a huge factor of environmental resistance. Because these can keep being renewed, but for most populations, space just can't keep adding. So environmental resistance falls into two categories, what we call density independent. Density means, think about like amount. If you have a dense amount of mice in an area, it means there's a lot of them in the area. Independent means this kind of environmental resistance is going to hurt a small population as much as it's going to hurt a big population. So this kind of environmental resistance is really, really rough. So again, density, think about it, it's like the amount or number of individuals. And if you have a population of 100, or if you have a population of 1 billion, this thing is going to hurt a small population as much as that will hurt a large population. So the size of the population, it doesn't matter. It's gonna get really hurt by this kind of environmental resistance or this environmental factor. Density dependent, that means that as you get bigger, you're gonna feel the effects of this kind of environmental resistance more. So like space, for example. Small population that has, let's say there's a population of 100 mice out there, and for some reason they're just like, oh, we'll level out at 100. We'll stay about that, so we all have a lot of space out there, as opposed to if you had like 10,000 mice out there, then the amount of space that they have is much smaller per individual. So the size of the population is going to be affected by this kind of environmental resistance. So density independent, weather events. So if you live on an island and a tsunami comes and you have a nice little stable population of 100 mice and that tsunami comes and kills everybody. Or if you have an unstable population where you're just like uncomfortable and crowded and you're fighting for resources, that tsunami comes, wipes everybody out. So weather events often just can have a big effect on, doesn't matter the size of populations. Humans. Let's say we decide that we are going to use the prairie now for a parking lot or a new building. Doesn't matter if we have a nice stable population of mice or if we had a ton of them. They're all gonna get their habitat gone because we're gonna build the building. Could also be pollution effects, pesticides. A lot of building for humans though. And often the building causes these things too. All right, density dependent. The size of your population means that you have overcrowding, means that predators can see you better. If there's a 20 elk, this pack of wolves is gonna be like, oh cool, let's focus on one. Like they're gonna find the elk, right? The elk are running around, they're like, oh, look at that group, we can see them. Whereas one might go in the forest and kind of hide a little bit better. It's not as obvious. So predation is definitely a density dependent factor. The more individuals in a population, the more prey available, the easier for a predator to see them. This is a really interesting study that was done on lynx, which is kind of like a medium, small to medium sized cat, and hares, which are rabbits. And they tracked them for 90 years and saw the effects on the predator, the rabbit, on the prey, the hares, over time. So when we take a look at the hares, they're the blue. So to begin with, predator population is low. The lynx population, there's not a lot of predators around. So when predator population is low, that allows the prey to grow. But when the prey population starts to grow, the predators are like, we have a lot of food to eat. So then the predator population starts to grow. Now when you get a lot of predators, that affects the prey. So the prey population comes down, something happened with the predators, they go up a little bit. But you see that as you have more predators, eventually the population of the hares or the prey starts to decline. When there's no more food around, predator population begins to decline. The hare, prey population starts to grow. Soon thereafter, predator population has food, they grow. Too many predators causes the prey population to go down. So you see this like lag effect of the predators. The red, their graph is very similar to the prey population, the rabbits or hares, but it just goes a little bit behind. And they definitely, in terms of predator and prey, have an effect on population size over time. Here's another study that was done on weevils, like little bugs, and wasps. They're a predator. And so you can see that when the predator population was high, it affected the prey population to go down, high, low, prey. When the prey are low, the predator population starts to decline. You don't have many predators, your prey population is like, whoo, nobody's around, we can reproduce. Soon thereafter, predator population rebounds, prey population begins to decline, then predator population begins to decline. Parasites. When you live and you have a lot of individuals in the same place at the same time, they can spread diseases very easily. The idea of a parasite is that the parasite doesn't want to kill their host. They want to live off their host for a long period of time. They might damage the host a little bit, cause the host to get a little bit sick, but they're not trying to kill the host. Some of you may be parasites to your families. If you are living at home and your family's like giving you food and a space to live and gives you money to get clothing and all of the essentials that you need, are you going to go and kill them and stop your income, your support? No, you're going to be like, I'll be there. Are you maybe the most easy thing to support in the world? You might have some financial stress on the family. Might be a little moody sometimes because you have a stressful life, right? So you're going to keep your hosts alive. The tapeworm is one example. Tapeworms can live inside of their host for 10, 20, 30, 50 years. Some people can die and have had a tapeworm and never even know it. Yeah. Competition has a huge effect. When you are competing for limited resources, things can get a little bit ugly. We're going to look today in lab at different survivorship curves. Survivorship means the number of individuals who are surviving over time. You can look at it as like glass half full or glass half empty. You could say the number of individuals surviving over time, or you could say the pattern of death over time. You will see today when you take data, if what you're taking your data on shows a late loss, type 1 curve, a constant loss, type 2 curve, or an early loss, type 3 curve. So late loss curves. Late loss means that if you can survive to old age, or at least if you can survive past the juvenile stage, you probably survived to old age. It's a convex survivorship curve. So as long as you can get past that juvenile period, you'll probably make it long. So you have a lot of individuals and then not many, or you have like a lot of individuals surviving later in life. Okay, so let's think about organisms. Which organism might be characteristic of surviving to very late in life? So maybe, like we know sea turtles live long, but if you remember the sea turtles, they didn't have a real easy time surviving in the juvenile stage. A lot of them died, right? Yeah, a lot of them.
I would say bacteria.
Yeah. So humans are a good example. A lot of organisms who are big. Because when we're talking about organisms who are big and live a long time, here's the distinction between a sea turtle and a human, right? They both, we have them, we both have the ability to survive a really long time. But in the juvenile stage, the survivorship of the juveniles is really hard as a sea turtle. So not a lot of them survive as juveniles. As humans, we protect our juveniles, right? Mom wasn't around to help her hatchling sea turtles, her babies, to get to the water and live. She lays her eggs and she's like, I'm done, I'm out of here, good luck. Whereas humans, we take a lot of care to our offspring to ensure that they make it past the juvenile stage. So that's a key thing. Oh, I guess I gave it away. So which one, which one would be the correct answer? So when we're talking about type 1, late loss, do you have many offspring and you don't protect them? Or do you have few offspring and you really protect them? Yeah. So when we're talking about late loss is that you don't have a lot of babies, but the babies you do have, you're like, I'm gonna get you to a point where you can live to old age. So we have a lot of survivorship at the start. Key thing is few offspring. As groups of individuals have tons of offspring, like imagine if you had 1,000 offspring. You were a species that had 1,000 offspring at the same time. Could you ensure that all 1,000 do well? No, that'd be tough, right? All right, constant loss. You have a constant death rate. This is hard. Every day, these kind of species may be faced with death. Or not. But every day you wake up and you're like, this could be the day. Be the day I die.
Wait a minute.
Yeah. The straight line survivorship curve, but it goes on an angle, it's a curve. So birds who migrate. If you're going from Canada and you have to fly the next 6 months, or the next, like, let's say 3 months down to the tip of South America, every day, even though you might know the path because you can use the stars to navigate, every day you might be faced with danger. That you're like, okay, I'm gonna get here, I'm gonna look for a place to live for the night, to camp out. Hopefully I can find some food that I like and I need, and hopefully nobody eats me. So you got a lot of challenges every single day when you're a migrating bird. Bacteria. They find a nice, moist, warm place to grow. That's what they need. Early loss means that you have a really high initial death rate. Sea turtles. Anything that lives in the ocean, typically, when we're talking about like fish and invertebrates. Sea turtles. Not the big mammals, but most species in the ocean, most insects who just have tons of offspring and they're like, good luck everybody, I gotta go find food. This is concave. So large number of offspring, no parental care, maybe a little bit, but pretty much none. And as I mentioned, a lot of invertebrates in the ocean, fish in the ocean, sea turtles are a big species that are an exception. Plants, they're just spewing out pollen, hoping for the best. And all of these are early loss, meaning that they have a good chance of dying early in life. So here can show you like humans, right? Most humans are protected so that we have a lot of individuals here and a lot of individuals survive to older age. Migrating birds, every day, they start out, there's a lot in the population, every day some die, some die, some die, some die. So that you have death constantly. And then if we're talking about like plants or invertebrates or fish or sea turtles, that you have a lot of death right away. And then those who survive will make it to old age. So let's see how much I can get done in the next like 5 minutes. All right, so what about the human population? We can defile this. As I mentioned before, that humans, and if we know anything about humans, we know we're growing, right? Numbers keep ticking up. You may have seen in your lifetime, 6 billion to 7 billion, we hit 8 billion. There's a lot of individuals, we just keep going. But we know we have an exponential growth happening. Why? Technology in so many different ways. Technology can be food technology, living technology, energy technology. We have a lot of different technologies to protect us, medicine. We have the ability to manipulate our world so that we have a better chance of surviving to older age. But what is the cost to other species as well as the environment? So over time, what we saw is we have this graph that shows that humans were at a pretty low level for a long period of time. And we start to go up, up, up. Bubonic plague takes us down a little bit, and then right here, the Industrial Revolution happens. And we see a lot of machines take us up to, we're past here, right? 8 billion. By 2037, we'll have 9 billion. By 2057, we'll have 10 billion people. More developed countries, meaning that they have more access to technologies. They make up about 1 billion. Less developed countries, and this is kind of frustrating because you have countries that have cities that are super developed, and then you have the countryside where it's really not developed. So this, we really should say like cities more than countries, right? Cities are countries that have big cities. We have been able to evade environmental resistance, unlike most natural species. We can pack cows into a factory. We can give them growth hormones to get beef faster. We can change the genes of our food so that they don't get eaten by insects. Vaccines. So much that we can do. The biggest impact on technology was in our early, kind of more, like, we're starting to become more human and less like other primates, was that we began to use tools. That was our earliest technologies that gave us an advantage over other organisms. And once we started to learn how tools could make our lives more efficient, we just started to learn and change and learn and change and learn and change. And so that we could do manipulations to cooking with fire, keeping warm with fire, where we build. We can build houses and invade the environment, put on clothes.
Is that why it seems like scientists are a lot tend to be interested in when animals start using tools, like when you see apes start to use tools, like is that why that's kind of like a big deal?
Yeah, and that's why archaeology is such a huge field, is because people are so interested in like the changes in technology over time with humans.
There's Homo habilis.
Yeah.
Homo habilis is a tool.
So it leads us here. And some of it is like, oh, this is gonna be great. Love the idea of renewable energy sources. We don't have to keep going to fossil fuels. Fossil fuels also have a lot of like bad environmental impacts. Granted, it's not all perfect here. You still have waste and you have energy to make this stuff, so you have to be a lot more cognizant of thinking like, this will save us. Well, there's still like waste and things that happen in the production of this. All of these things have helped us change what we can do. Okay, so we have just like, I talked about a lot of this already. Biggest idea is that these technologies that we have help us to not die so young. We can kind of understand a little bit about how long we should really be living by your metabolism changes. So a lot of you are starting to experience the like, can't eat as much as I used to be able to eat, because your metabolism goes down. And that gives us the idea that we probably didn't live that long. But we can change that. We've got lots of medications and things to change that. A little bit about what should our carrying capacity be? one of the things that we look at in terms of the human population is TFR, the total fertility rate. Sometimes it's called RLF, the replacement level fertility. And the idea is that if you have a mating pair, that they should only be contributing 2 individuals if we want to start to level out our population, right? You are you're a mating pair, you each replace yourself with 2 children. Humans, we have an average of, I think it's 2.47. In 1965, it was 5. People were having an average of 5 children.
Is that a baby boom?
Yeah, baby boom. That's why they call them the boomers, because they started to pump out kids. So this is kind of an interesting graph that shows you over time what our RLF was. That it started out like in the baby boom about 5, and now we're getting down to about 2.3 on average, but a mating pair is 2 individuals. So we're still above, and if we have 8 billion people who are making 2.3 people per mating pair, we're still above the 2 that we should be to level out. World population growth, you can see that the RLFs or the fertility rates are different depending on the countries. You have a baby boom in Africa for sure, but Africa's not a country, it's a continent of a lot of countries. Age structure growth shows you how many individuals in a population you have pre-reproductive, babies, when they get into reproductive age, and your post-reproductive or your elderly. In a lot of countries that have great amount of technology, or even in cities, you're starting to see shrinking. That you're not having as many individuals reproducing anymore. And I'm sure a lot of you, even like my son said the other day, he's like, I don't know if I'm ever gonna have children. And that's like a whole new thing, is that people choosing, making a choice, as opposed to being pressured to have children. So we can have a lot of growth, like in the continent of Africa, you have a lot of young people being added, which means that eventually this is gonna get bigger, and this is gonna get bigger. So here you can see just like different countries like Kenya, Nigeria, Saudi Arabia are adding a lot of individuals to the population. You see slower growth in the United States, Australia, Canada. We definitely politically are hearing a lot more about not allowing people to choose to not have children because they want more population over time. And then you have some that are shrinking. And some that are stabilizing completely, and then some are shrinking. All right, so this just gives you an idea of Asia. I think India, for example, maybe overtaken China recently in terms of population numbers, that they both have over 1 billion individuals.
I think last time I was doing a research about India, it was like have some 19% of the pollution around the world.
Yeah. And here's just the United States.